Okay, so let's jump right into the next topic, which is hypothesis testing. Um, so far we have covered what probability distribution is, what a random variable is, and all these things. But in our research and our day-to-day life, we're not flipping coins, we're not rolling dice, we are doing much more research. We are going and collecting the actual data, doing the real groundwork. And for that, how do we know if something is really true? This is the first thing that one has to really think about when we are addressing any kind of a claim. For example, this picture, I found it from a random WhatsApp forward from one of my family groups, where let's say my mother, okay, she claimed that yeah, wear silver rings. It's very important. It increases your fortune, and she said things like, yeah, it's very good. If you're a woman, you have to wear a silver ring. It's good for your health. And sometimes when you look at things like this, you're often wondering, what? Like, this makes no sense. This makes absolutely no sense. Why? What is the proof for it? As a scientist, you're always wondering, who is claiming this? Who is saying these things? So, yeah, so people make claims all the times, and statistics is the bigger field that we are all associated with as social scientists, as human beings generally, to make us have the decision if this is real or if this is just a simple coincidence, like maybe 3 people, 10 people did it. Okay, say 100 people did it, and they all got lucky, and or if it's just some random thing that people are just saying. So this is one of the main reasons we need to know. We study statistics, and the process of it is, yeah, you get the data, you make a study, you get the evidence, and then you're making decisions. The decisions, these are not opinion, they are decisions. They're statistically significant decisions. They're based on the data. And we all know, including ourselves, we are quite bad at judging randomness. I mean, I can do a juggling task one day, and I can be extremely good at it, and then I say I am the best juggler in the world. But that's not true. I have to do it. I have to do it a million times. I have to prove it to several people, to many people in the world, that I am really good at juggling if I do it so many times. So statistics helps us to avoid bias and to avoid overreacting to small samples. And this is extremely, extremely important of what your sample size is, and how you react to that sample size. Is collecting data from 10 people in a whole big population of India, is that enough? Things like that is what makes us question yeah, why we need statistics, also as to how we look at our data. And before any of this, we need to make what a hypothesis is. So when we are entering any kind of a field, we got to make an educated guess. So a hypothesis is an educated guess about how the world works. So you get an idea, you put it into words, you put it into statements, and you put it into statements of true or false, of 0 or 1, like how we saw these different probability distributions. You get an idea of what the data might look like, and then you go on to ask your actual scientific questions about it, like what you're going to measure, how you're going to measure it, and what your data will eventually look like. Are they discrete variables? Are they continuous variables? Is it just, you're doing a test and you're just looking at success or a fail? Or are you actually collecting like numbers? Somebody suggested here the conflict score, right? Like that's a count. So you're getting counts, like you're getting 326, 558, and so on. So these are different counts, and then visualizing it as any kind of a bar graph, or any kind of a visualization form of it, and then applying a statistical test to determine if this is actually a true thing about the question that you asked. If the statements that you suggested, that the hypothesis, the educated guess that you made, if it is actually a true thing about how the world works, or what the question that you asked. For example, the average height of, you just make the statement, the average height of this class is 5'5". So this is just a guess that you're making. It is not the truth. To say that this is the truth, the average, the mean is this is the truth, you got to collect the data, you've got to do the groundwork for it. Or women working in self-help groups improve household decision making. So how do you come to this? How do you just make the statement? You can't just make it. So you need to go somewhere, you need to get the data, you need to go collect. Maybe you need to see how women are making decisions. What does a decision mean? What is the age group of the women? Which part of India, for example, are these self-help groups in? Things like this. So you need to make a lot of these, put all of these things together. But in statistics, we don't just test one hypothesis, we test two hypotheses. And so I present the two hypotheses to you, what is called a null hypothesis and an alternative hypothesis. So in the beginning, of course, it might feel like what are these statements and stuff. But do your research and you start doing your research, you start off with what is called the null hypothesis, which says that you say that you always start by saying that nothing is happening. There is no effect here. There is no difference as such. I'm testing, 10 different people. I don't think there's a difference here, is what you start with. Start by saying, you say that I think there's no difference. And oftentimes you prove the null hypothesis is true, or you prove that the null hypothesis is false rather, and then is when you accept the alternative hypothesis. For example, I say, the average height in this class of 21 participants is 5'5". So this is my hypothesis. And the null hypothesis is that, yes, there is no difference as such. Yeah, this is the average height. That is it. And you accept the null hypothesis and you say, yes, this is the truth with all your data, and then you move on. Oftentimes that may not be the case. Maybe the average hypothesis actually, maybe let's say we're all taller people, and the average height of this class is say 5'7", but that's not the truth. So what I said in the beginning, 5'5", is not the truth then. So then you say, okay, I reject the null hypothesis and I accept the alternate hypothesis, where I say that the average height in this class is actually 5'7". Yeah. Okay, so yes, you always start by assuming that the null hypothesis is true. And a clear way to go about this, you can think of it like an easy picture is a courtroom, for example, where the null hypothesis is the convict. That's the criminal, like who you're putting to jail, or who you're testing, who's testing in front of the judges. The judge is the you, right? You are going to say, are you going to jail or not? And and the evidence, so the evidence that you collect. So of course you can have evidence for the criminal or against the criminal to say if he is guilty or not. So if you have evidence to say, yeah, like I saw with my own, if somebody is saying that I saw with my own eyes that, yeah, he killed this person. So of course, then the criminal goes to jail. And the one against the criminal would be that, no, he said, this is not the person I saw, there was another person that I saw. So it's against the criminal. So similarly, it's your experiments and that you do, and the data that is generated from the experiments, which provide the evidence to either push your hypothesis for the hypothesis or against the hypothesis. And you are the one who is making this judgment. So it's extremely important that you always make the right judgment. You always assume that the null hypothesis is true, which means that the criminal is not guilty until he is proven to be guilty, until there is enough evidence to say that, yes, he is guilty, he has to go to jail. No, until then, you cannot say that he just goes to jail because, I don't know, one person saw that, I think he saw in his dream that, yeah, he killed. You can't say that. You need to have the proof, okay? So, yeah, the procedure for this is, of course, you assume that the null hypothesis is true, you collect the data, and you say if the evidence is strong. And if it is wrong, yes, you reject the hypothesis, put the guy in the jail. If not, then no. Then you fail to reject the null hypothesis. Then yes, then it's somebody else who goes to jail. So we never try to prove the alternative hypothesis directly. So you never say that this guy is guilty. Like it's always innocent. Like this is yeah, he's innocent is the basis. So you always try to prove the or null hypothesis and then only the alternate hypothesis. Okay, is this clear so far? It sounds pretty straightforward, but can get also quite confusing. Okay, so now it's your turn. Now we have a pack, like usually packets of gems, for example. And my claim here is that gems has equal number of red and blue candies. What do you think is the null hypothesis, and what do you think is the alternate hypothesis? You can put it in the comment in the chat. Any answers so far? Null, it doesn't. Alternate, it does. What does that mean for the red and the blue candies? Um, so once again, the null hypothesis is something that where you say that so you usually go with the claim for the null hypothesis. So if I say it's equal number of red and blue candies, and okay, maybe I just go on to the next slide and I can reveal the answer to you and we can actually think about it. And if you have any questions, we can talk about it. So the null hypothesis, if this is my claim, then my null hypothesis is this is just a hypothesis. You don't know about if they have equal numbers, if blues are more than red, if it doesn't, if there is, we didn't talk about orange at all, Shiva. But so the null hypothesis for this particular claim is that the red candies are equal to the blue candies in the gems packet. And the alternate hypothesis is that the red and blue candies are not equal to each other. Yes, so the null is that there are equal red and blue candies, and the alternate is that no, there are maybe more red candies or there are maybe more blue candies. But how do you know this? You can only know this if you, actually count the number of red and blue candies in, I don't know, maybe 1,000 gems packets. Is this clear? Can somebody else come up with another hypothesis? Maybe you can type it in the chat. Maybe one's very easy null hypothesis and your claim, your null hypothesis and an alternative hypothesis.
I can type one in the chat and I will also say, I claim that all the participants of this winter school speak fluent German. This is my claim.
So what is the null hypothesis and what is the alternative hypothesis?
Let's do only the null hypothesis.
Let's do the null hypothesis.
Yeah.
Anybody? Anybody? Come on. It's pretty straightforward. Yes, there is no difference. Okay, you're giving another example. There is no difference in workforce participation. Yes, null participants fluent in German. No winter school participants speak German. Null hypothesis, all the participants speak fluent German. think there's a bit of confusion in this group today.
Yeah, I noticed too. So one way, I think how if you, Kavita, if you go back to the previous slides, but I mean it's the same thing, but
This one or this
no,
one?
the one after without no, it was I think it was all right. So you can the null hypothesis is the claim.
Yeah.
It's identical to the claim. So I claim that all the participants of this winter school speak fluent German. The null hypothesis is that all the participants of this winter school speak fluent German. This is the null hypothesis. It's exactly identical to the claim. Anything different than the claim is the alternative hypothesis, but at that point, it's not important anymore, right? So
No.
the null hypothesis is, in this case, there's no difference between the people inside the group. Everybody has the same baseline. In this case, everybody speaks fluent German. In the candy case, all the candies have equal numbers. No
Yeah.
difference, nothing special is happening, no effect. This is most often the null hypothesis.
Yeah.
Let me read the other comments.
There are no difference characteristics of null hypothesis. Is it related to the claim or is it related to the eventual outcome? It is often related to the claim. Yes, it's not related to the eventual outcome because you do not
Absolutely
know the
not.
eventual
Yeah.
outcome. Yeah, because you only make the decision of the outcome based on yeah, framing your null hypothesis. And after getting your data and analyzing your data, you prove that, there is a change in the outcome. And to accept that change, you reject the null hypothesis and you accept what is called the alternative hypothesis, which is the the other hypothesis that you make to say that there is a change or something is happening. Should we spend some more time on this to understand this? Is it clear? Do you maybe have one or two more examples and we can maybe state the null hypothesis and the alternative hypothesis? Can you explain it by thinking?
Let's one more. Yes, I have another one. I think it's because for example, just as a I was reading again
Yeah, I think there's
the
one.
chat. I claim that all
I
human
claim
beings
that
read.
all human beings read animal behavior anthropomorphically. Okay, so that's your claim. Great. Okay. So what would be the null hypothesis then? That yes, so that you don't think there is a difference in all human beings reading or studying. Yeah, so all human beings read animal behavior anthropomorphically would be the null hypothesis, and what would be the alternative hypothesis then? So if you reject, so you can get to the alternative hypothesis if you reject the null hypothesis. So you collect your data and then, you see that no, there are people who don't read animal behavior anthropomorphically. So like might not. Yeah, that's a good suggestion. Yes.
I was thinking because another way of I was thinking how in the past I learned about the null hypothesis, right? Because I was thinking now that it's always not what you would expect in a
Yeah.
way, right?
Yeah.
So uh, it's it's always so I think I remember one of my teacher once told me it's always the boring one.
Yeah.
So if you expect some change, some differences between two groups, for example, somebody asked like, can we take an example with two variables? Like you expect two groups, and you say one group
Mm.
has one group of humans reads animals anthropomorphically, and the other group of humans does not, let's say that. And the null hypothesis, it's always the boring version. So no, there's no difference. So there's no effect. Yeah. So this not happening. Nothing is happening. While anything like the alternative hypothesis would be anything else. So yeah, there is difference. Or yes, we do behaviors. Yeah.
So,
Let's see.
but to accept the alternative hypothesis in the beginning itself would be false, actually, mainly because if you make a statement in the beginning itself, saying that yes, there is, so let's say, taking like before and after taking a medicine, for example, a drug, so you test some participants before they take a drug, and then they take this medicine, and then I don't know, maybe something happens to them, and you check the after. And if you, in the beginning itself, you claim that yes, there will be a difference, then you cannot proceed with the scientific study saying that there will be a difference. You got to accept, because you can't. Of course, you predict the unknown eventually, but you can't go with the statement of saying that this is the truth. The unknown cannot be the truth until you actually prove it.
Prove it.
So, yeah.
I think then it was my fault. I think I said something wrong, or I miscommunicated, because I said it's always the claim. What I meant, it's not that it's always the claim, it's you have to start from the claim, right? So like Kavitha said, let's use this example. Let's use this example of the sleep hours, because I see that's going on a lot. Okay. We are studying whether sleep hours affect class performance, right? There is no claim here. Sleep hours affect class performance. Affect, could it mean positively or negatively? Let's say that the more you sleep, the less you are performative. So the increase of sleep hour reduces your performance. Example. So in this case, the null hypothesis would be that the sleep hours do not affect the performance, right? Because it's always the most basic assumption that it's also what you wouldn't expect, right?
That you don't see anything
Anything
special or
happening.
anything, crazy or fun happening. Like it's like
There's
there is
no
no
effect.
difference. Like Cecilia said, it's the most boring thing. Like
Burden.
sleep hours and class performance, there's no effect, like only until you do the study and look at the data and then say that maybe there's something happening, and then you say yes, something is happening. Sorry, you've raised your hand, Ajay.
Yeah, just to add in,
Yeah.
hopefully maybe that is in the coming slides, but it helps a lot when we divide and also understand hypothesis from the directional hypothesis and non-directional hypothesis. Like when we have non-directional hypothesis, that time we only see whether effect is there, then alternate. If not there, it is null. But when we claim effect is not there, and in alternate we say effect is increasing, then it is directional. And if we don't say like anything, we just say effect is there, then it's non-directional hypothesis.
Yeah.
That is also one division. From that perspective, also we should also understand the hypothesis. That will also give more clarity, because sometimes from the previous research we know what actually is the effect is going to happen, whether it's increasing or reducing. But when we are not sure, that time we will take the non-directional. That is, effect is there. But we have to make, as was one participant said correctly, we have to make all these claims before testing the hypothesis. We cannot change the claim after testing the hypothesis.
Yeah.
Even nobody is watching you, So
Always.
that's a
Always.
big
Yes.
ethical question when it comes to the hypothesis testing. So
Yes.
thank you.
Yes.
No, this is a very good point, and
That's
it's very
true.
important to always have it in mind. You can't collect the data first and then have hypothesis. Never do that. That's quite, I mean, it's bad statistically speaking, because you can't go like have a look at the data and then formulate hypothesis. Yes, thank you for that because it's important. I put another example. It's the same example Kavitha made, or the same example of the sleep hour, but this is what Ajay was talking about. In this case, I have no directionality. My claim is I believe this drug works. Does it make it better? Does it make it worse? Doesn't matter. I believe it works. The null hypothesis will be no, it doesn't. As simple as that.
Exactly.
Anything else would be an
The
alternate
alternative
hypothesis. An
hypothesis.
alternate
True.
hypothesis could be, yeah, the drug increases sleep
Mm.
quality or
Mm-hmm.
decreases sleep
Mm-hmm.
quality
Mm-hmm.
or increases performance, decreases performance. Anything this they can be
Mm-hmm.
different alternative
Yeah.
hypothesis, but the null hypothesis will always be no, there's no effect.
Yeah.
There's no difference. For example, in this case, this new drug works, null hypothesis, there's no effect. I think this slide summarized it quite well. Like maybe you can think of it this way. When you make a claim, you think the null hypothesis is always no effect, no difference between group. Nothing is happening. There's status quo. Yeah.
Yeah. Yes. Okay. Maybe we can move on if this is clear. And I think by moving on, we will also get to how we are proving it and all of that. So how do we test it? So of course, you have your subject, like Ajay said, you have your previous research, you're on the shoulders of everybody else who did these research. And then you come up with a question, right? You like the drug testing, for example, you think whatever chemical formula X is unique, and you think yeah, you want to get into it and understand what it does or what kind of an effect it has, and then you formulate your hypothesis. So the basic null hypothesis formulation would be yeah, probably it doesn't do anything. So it doesn't do anything is the hypothesis. And of course, your alternative hypothesis would be, yeah, this drug X is, I don't know, it increases a lot of sleep for people, maybe. So it's good or bad or whatever, you know. So you go on to do a hypothesis test. And to do the hypothesis test, you need to collect your data for it. You need to go do your research, your groundwork, all of that. And then most often with the hypothesis test, you get to see what we saw already, like you look at a probability distribution of how your data, is arranged in, space, or how the population is organized for that, from the data that you collect. And like what kind of statistical tests, depending upon a discrete data, continuous data, if they are counts, as somebody suggested, if they are like just the success or the failure, as we saw, the zeros and the ones, what kind of a hypothesis test, what depending upon the different variables that we are looking at, be it categorical variables, be it just count kind of variables, how can we make these kind of a test? And then only that you can make a conclusion. So like here, of course, with the hypothesis test, we saw it in the bell curve earlier, like, yeah, and you make a bunch of tests, and it's likely that your observation probably falls somewhere here, and it's unlikely, like Cecilia explained earlier with the weight example. It's very unlikely that, yeah, maybe there are people who weigh, I don't know, 400 kilos or something, as compared to a normal 50 to, I don't know, 100 kilos, So of course, those are very unlikely observations. And this part about hypothesis testing is actually important, mainly because one can get into different kinds of errors, as we call it, in statistical terms, because you can only reject a certain, like a hypothesis with a certain probability, um, because different errors can occur. So, for example, like say you have the criminal, right? Like you can't reject the criminal, like you can't rather send an innocent to the jail, like I said earlier, without having enough evidence, right? So that would be a type 1 error. If the null hypothesis is rejected, although the null hypothesis is valid, then that is a type 1 error. And a type 2 error is when the null hypothesis is not rejected, although the alternative hypothesis applies. So maybe we can think of this with the examples that we followed throughout so far. So maybe the first one, the easiest one could be let's say the convict, the criminal, you know. So a criminal is the null hypothesis. So probably he hasn't done anything. So that's the null hypothesis you go with. The criminal has not done anything, okay? And you collect your evidence. You see people who've seen him kill or not kill and whatever. You collect your data on this. And so what does a type 1 error say? If the null hypothesis is rejected, so you say that he did not he killed rather, although the null hypothesis is valid, although that which means that he is innocent. Although he is innocent, you claim him to be a criminal, then that is the biggest statistical error. That is a type 1 error. Yeah. And if the criminal is actually a criminal, but you do not reject that and you say he is innocent, then that becomes a type 2 error. So it's still an error, but it's a second type of an error. So what you're doing is not correct. So do we want to think about this with all the different examples, the sleep, the drug, I don't know, the other examples that you shared here? Like, do we want to go over this? Just for like understanding, it's of course it's
maybe one or
extremely
two
confusing.
examples.
I also get confused with it most of the time. So let's just,
I will put it in the chat.
yes.
So let's start with the drug because it's the closer to me.
Yeah. So the null hypothesis is that the new drug X does not work. And the alternative hypothesis is that new drug X increases sleep, So what is a type 1 error then?
I typed them in the chat so you can see.
You can think it takes a bit to think about it because it can be a bit confusing. Or maybe it's straightforward. My bad. But yeah. So type 1 error is.
So what you should do now, I gave the claim, I gave the null hypothesis and the alternative hypothesis. All right?
So what could be the type 1 error?
So now you type 1 error, the drug does have an effect. So we reject the null hypothesis that it has no effect, but in actuality, it does not. So a type 1 error does have any effect? No, it's so the type 1 error is the drug. We say that the drug does have an effect, but in reality, it does not. Am I correct?
Yeah.
Kavitha, check on me.
Yes. So the drug does have an effect, but is this type 1 error?
Yeah.
Yeah.
So we say after we collect all the data and do all the tests, we say, yes, the drug has an effect. So we reject the null hypothesis, but in reality, we did some wrong calculation and the null hypothesis was correct all along. Let's do another example. Sleep hours affect class performance. Oh, there's a new message. So give me a second, I type in the chat. So claim sleep hours affect class performance.
So just a moment, Chichi.
Yeah.
So it's not about, the type 2 error being, because you can't call it a type 1 or a type 2 error without like what is happening versus what you think is the hypothesis, what you think has happened rather, so I think that's the main thing here because how can I put it? Like the drug thing itself, like I see one of you have typed that type 2 errors that drug has no effect. But yeah, I mean, that could be so that is the null hypothesis, right? And maybe
What's the
it,
outcome?
it's
Yeah.
the all, yeah, it's the outcome, exactly. And so it only becomes an error if you have accepted the wrong outcome.
Yeah. Yeah, that's a great way to put it.
Yeah.
Yes. So
Yeah.
this happens all after you collected the data and after you, yes, you reject or accept one of the thingies. And yes, this happened all after. So claim sleep hour effect cluster performance, and the hypothesis it does not. And the alternate hypothesis it does. So this is the scenario.
This is a
All
scenario,
right.
then um, you collect your data, you get all the things, and if, of course, if it does not, if sleep hours does not affect, then of course it goes with the null hypothesis. If it does, then you reject the null hypothesis, you kick it out, and you accept the alternative hypothesis. But then sometimes you can make an error. And the error, what could be the error in this case? So the type 1 error is, of course, when you
It does affect. Yeah, but you miss a piece. You miss a piece.
Yeah.
You miss a piece because how Apurv, how you framed it, it's just half of the story. Okay, type 1 error,
Yeah.
it does.
But in the reality, it does not. Yeah, exactly.
This is, I will put
This is
Kunal.
the drug has an effect, but in reality, it doesn't have. That's true. Yes.
I put
That's correct.
thumbs up for all
That is
three.
correct.
Super.
So what is the type 2 error then for the same question?
You just switch it around.
Yep. It does not, but in reality, it does. Yeah. Good.
Super.
So, I mean, these are some things that we usually don't think about, but it's a good practice always before you go on to collect your data for your research, to frame the hypothesis, frame the null hypothesis, frame the alternative hypothesis, think about what your data might look like, and like how you could make this error, like what are the possible ways that you could make this error, and keep that in mind before you actually go on to do more and more statistical tests. Because once you enter the world of statistical testing, you tend to just believe what the data says. But then if your hypothesis itself is wrong, if you have made these errors, if the basement itself, foundation is weak, then the building is also weak, so it's very, very important to make a note of all of these things and only then proceed on to your statistical tests and all the conclusions that you make from the statistical tests, because it's super easy, because we will go on to the next slide, which is on the p-value and all that. So once you have the p-value, it's super easy to say, yeah, there is an effect, there is, yeah, something has changed, yeah, like I'm going to win the Nobel Prize. Not necessarily, always keep
Always
track of these things. Yes, yeah. Okay, so I think we can move on then. Okay, so that leads us to the p-value. And the p-value is important because it is the probability of seeing data this extreme, if the null hypothesis is true. So if you say that there is no effect between a drug, the drug, and you look at your data and you get this p-value as such, which is calculated. And yeah, so that is the probability of how you say that the null hypothesis is true, and it is not the probability of the null hypothesis is true, and then not the probability if your result is wrong. So you can't just judge just because it is true, or just because your result, it doesn't say that your result is wrong just because you get a higher p-value. It is just that you can see the data this extreme. In other words, I'll finish this and then we can think of examples and all of that. And we'll also do a lot of this in the R, which is to follow a bit later. But so the value that people usually chase, that is 0.05. Yeah? If the p-value is lower or equal to 0.05, then you can reject what is this null hypothesis. Then you can, for example, the 0.05 is the 5% chance. So say you have you have 100 people, right? And you're looking at, like I said in the beginning, heights of the class. And if you say the average height of the class is 5'5", yeah, so that is your null hypothesis. But then you collect your data, you do your groundwork, and then you find that we are a taller class, and the average height goes up to 5'7", and then you do a statistical test based on this, and you compare all these heights together, and you determine, yes, the average is 5'7" indeed, and your p-value also kind of shows you that yes, even the lesser, or how do I put it, like there is a 5% chance that people or rather 95% of the people, 95% chance that everybody falls into this, this average of 5'7" and nearby, and there's only a 5% chance that it doesn't happen. And then you reject the null hypothesis, and you say that, yeah, so people aren't in this 5'5" height, they're probably higher, probably 5'7". Am I getting clear on it? Chichi, do you want to jump in on this a bit? We are muted.
Oops. Yeah, I wanted to know if from the students if everything is all right, or if we need more examples, or
so we don't, so we only reject the null hypothesis when the results are very, very unlikely. So it
yes.
has to fall, like even if you take something like 100 people, even up to the 5%, which is 5 people
Yeah.
actually, of them have to fall within this average range of 5'7" height to prove that that they are of this height or weight or whatever that your question is, right? And only if it is lower, like statistically, which is the 0.05 mark, then you say that it's not the same, it is different. Is this clear, or are there
Maybe let's take
questions?
the example of the drugs again, because it's the one we built upon. So I say the drug the claim is the drug, how was it again? Let me see the chat. I believe this new drug works. Null hypothesis, the drug does not work.
Yeah.
And the alternative hypothesis is the drug does something. All right. I pasted them again in the chat.
Okay, good.
So if your p-value is, let's say, I collect my data, I do all my whatever blood samples, I don't know, whatever doctors do, and I come with some data.
I have put a value for you, p-value.
Yes, 67. If my p-value is 67, it means there is a 67% chance that this recovery was just like the drug working is just a coincidence.
Yeah.
Right?
Yeah.
So the results are not significant because 67% chance that if I see some effect, it's just a coincidence. All right? If the p-value is 0.03, there is only a 3% chance that the outcome is a coincidence. It's a very unlikely case that this outcome is a coincidence, meaning it's very unlikely that out of 100 people having this drug, that they would 97 of them will recover only by luck. All right, that's another way to put it. So the value is so small that it's impossible that it's only by luck. Almost impossible that it's only by luck. Can somebody say for this next example 0.06? How would you phrase it?
Is there an effect, or do you reject the null hypothesis, or do you accept? Do you accept it? Yeah. Yes.
Perfect, because it's really on the edge.
It's really on the edge. I mean, you
the
can
cut is
have a say
0.05.
in a paper that, oh yeah, maybe I need to collect 50 more people's data and then say that, then maybe, you know, it has an effect actually. Maybe it has a tendency to go in the other direction. So,
But there's also, could be
yeah,
some.
but then if it stays at 0.06, even if you collect, you know, data from 1,000 people, well, that's your life. It's reality.
It's life, yes, exactly.
Yes, yes. Okay,
And
so I
again,
think
the 0.05, it's convention. It all goes back to this shape of the curve and this very unlikely part. Because again, we use this 95% and the remaining 5 is the very unlikely case. And this cutoff is always 2.5 on the lower side and 2.5 on the higher side. And this is the 5, where the 5 come from. But it's a construction.
Yeah. Okay, so maybe we move on. So there's also this other concept called degrees of freedom when you're looking at your data, and how much this data can vary. So of course you can have a total number of data and it can all have values. And this of course comes in when we look at other tests in ahead, like the t-test and the chi-square test and so on. And it tells us, how many values are free to change. For example, if you know the total and some values, the last value is forced and it's not free. And the best example for this, the way I learned it, is a triangle. You know, so a triangle can have 3 angles, right? Like it's a sorry, it's a triangle, 3 degrees, right? And and it must always add up to 180 degrees. That's the rule of a triangle, right? So if say your first degree is 11 degrees and the second degree is a 15 degrees, then the third degree must add up along with the other two to form that 180. It has to fit the total to make it a triangle. Otherwise, it's going to be a straight line. That's it. You know, it's going to be like a weird open line, and that's about it. So most times when we collect all like data and we frame these hypotheses, we also need to know how much space is there for this data for it to be for it to give a bit of movement when you collect the samples. Like when you collect the samples, if you've collected only 3 values, then you have only 2 degrees of freedom. So it's always n minus 1, n being the numbers that you collect and minus 1 of it, because it usually has to add up to the total. So you have to lock in the nth value based on your previous values to fit your total. And we will, of course, you will see this as a value most often when we are running statistical tests, like, it spits out a value called DF, which is called the degree of freedom, or DOF rather. And when you are doing the statistical test itself, it might be confusing, like what does this mean? And and sometimes papers like journals ask that, like, what was your degree of freedom? Like, what was your sample size? What was your degree of freedom? What was your chi-square value? What was your p-value? So it's important to know what it is, and maybe we can understand it better with future examples. Okay. So to summarize this section for now, yes, we are with the data with generally in the world, we can always make a claim, but then the claim and has to be supported, right? And the claim has to have a statement, and you usually make a null hypothesis or alternative hypothesis, and we often design a test to test this claim. And by designing the test, we also accept and reject the possibilities of error. Again, these are just rules of how you formulate your data collection, your research pipeline, all of those things. You think of the p-value. The p-value, of course, measures if there is evidence to reject the null hypothesis, accept it, whatever. And then there's also the degree of freedom, which tells us how we can adjust for the data that we have, because there is little bit room for adjustment. Of course, the data tells us, it gives us this much space, but then it also shows us, yeah, you can adjust for this much of the data. So this is the main summary for now. I don't think we don't have, right, anything for the hypothesis testing. No, okay. So either we take another 5-minute break now and then jump to the next part, which is the t-test. We thought of combining this because it's quite I think it's better to solve these things on R directly. So we can come back after the 5-minute break or so, and then go over the concept, the logic of what each of this test is, and then immediately just jump on to the R. So do you want a 5-minute break or a 15-minute break? You can, Ajay, what do you think is better?
All are saying just 3 to 5 minutes. That's enough.
Okay, good. Okay, so we come back, yeah. And if you have any questions about any of these topics, please do share it in the chat in your break and think about it as well.